It is.
We record
yes.
and post all of our talks unless you do it.
In fact, I'm getting a message on this right now. So got it.
Yeah. All right, let me begin by welcoming Machiel Blok. So it's a pleasure to have you here visiting us for our Institute for Quantum Studies seminar this morning. I just wanted to give him a brief introduction for folks here in the Zoom audience that may not have met him before. So Machiel did his PhD at TU Delft, working with Ronald Hansen, working on mostly optics and some I think NV Center work there in Delft. And then he came to the US to work at UC Berkeley in the group of Irfan Siddiqui, and that's where I really got to know him pretty well in my time working with Irfan's group. And he was working there as superconducting quantum circuits. And then after he finished his postdoc in Berkeley, he then had a faculty position at the University of Rochester, where we briefly overlapped. And now he's been working on topics in quantum information, especially working with superconducting circuits involving higher than just 2 levels, working especially with qtrits and higher order levels and thinking about quantum information tasks. So we're happy to have you here today with us, Machiel. Looking forward to what you have to tell us.
Thank you, Andrew. It's really good to be here. It's nice to see some familiar faces and some new faces. So looking forward to discussions here. I was going to say it's really nice to be back in sunny California, but then I do know that you had some rough weather conditions. Actually, if it makes you feel any better, Rochester has had some rough weather as well. So let's see if I can advance my slides here. There we go. This was just a few weeks ago where it does get really snowy in Rochester, and I don't have to tell many of you this because you do know this. But just to advertise a little bit if needed, if you ever want to come back and visit, it can get really pretty even in winter. So we've had some very nice, lovely days, and the foliage is just beautiful.
So that's January 14th and December 14th.
It was, yes. I tried to pick the Rochester Twitter feed. If you're interested, actually, the university does a good job at updating the weather conditions. So you'll see that. And another reason why I put these pictures here is that indeed I do have some work from our group in Rochester, and I'm also going to present some of the work that I did in UC Berkeley. So it's going to be a little bit of a hybrid. And to make things more complicated, this fridge picture is actually the fridge of Professor John Machiel during the pandemic, who let me borrow his fridge. This is a sample that I took from Berkeley, and some of the science that we did on it is from the Rochester group. So it's going to be a mix. And mostly what I will talk about is multi-level quantum information processing. So we're interested in controlling the higher levels of the transmon circuit. And I will try to do a good job to give a little bit of a background on how the transmon works, how we control it, acknowledging that some of you are pretty expert in this. So I'll try to keep it brief. And please interrupt me if there's any questions. We can make this very informal, and I can skip over things or go into more depth if needed. So our motivation is to look at ternary quantum information and beyond. And when I say quantum information, it sounds very quantum information processing-like, right? Like building a quantum computer and that good stuff. It is part of our motivation. It turns out that it's actually pretty well documented that qtrits and higher level systems can give you significant scaling advantages in algorithms. But so far, I would say a lot of the theory work has focused more on qubit algorithms, just because those devices have been more available. I'll have some references later if you're interested, but really one of my hopes is that by building these systems, also the theory side of this is going to be taken more seriously, and we can see what we can do. But there's some documented advantages that are pretty significant. But I'm a physicist. I also like the physics aspects of this, and I just want to point out that there's a lot of quantum optics effects, very deep fundamental quantum optics effects, that are fundamentally multi-level driven systems. And so naming the outer towns, or stimulated Raman adiabatic passage, or even electromagnetically induced transparency, that's all multi-level physics effects. And you'll note that I have a picture here of an EIT paper that's from the 2016s. So that might surprise you a little bit, because this is an effect that goes way back. But this is actually an implementation on a transmon circuit. And so there's other examples of the upper towns effect and stimulated Raman adiabatic passage, all on transmons. And so we can study these kind of quantum optics effects on superconducting circuits. And that's also something that just excites me. Furthermore, if you think about quantum simulation, for instance, simulating gauge theories or spin-1 physics, you can do everything with qubits. Qubits are universal, so in principle, they can simulate any system you would want to. But some of these systems naturally have multiple degrees of freedom, more than 2 degrees of freedom per site. And so why not use a system that also has multiple degrees of freedom? Maybe you will be more efficient. And so one example that I give here where they do the opposite, this is from the Blok group, where they try to study spin-1 chain physics. But the way that they did it is that they string together a lot of spin-half particles to get the effective spin-1 physics that they're looking for, Haldane physics in this case. So my idea is maybe if you put a few three-level systems together, you can get the same physics more efficiently. So that's the hope, that's the dream, that's what we are looking for. Let's put that in practice. So focusing now on superconducting circuits, acknowledging that there's many other platforms on which you can do this. Generally speaking, qudits have been encoded in nonlinear circuits for a while now. If you're interested, this is some papers about the qudit advantages of quantum information science. There's these papers from 2012 and 2014 that show orders of magnitude improvement in error thresholds and efficiency for magic state distillation. And then there's this nice review on all the qudit advantages for quantum computing. But I wanted to point out that it's not new that we study these higher excited states in the transmon circuit. People have been studying their coherence times and doing tomography for over a decade now. And in particular, there's a set of papers that really uses this, for instance, the first next up excited state, so the 2-photon excited state, to aid quantum processing protocols, but not to encode information in them. So it's like a helper level. And that's already been quite successful with many more citations that are in the list here. But what was needed and what was not available for a long time is a universal set of gates that allows you to control qutrits and transmons to really do algorithms. So that's the first thing that I want to talk about today. That's the work that we did in Berkeley. So the plan for today is I will give a brief intro to superconducting circuits and show you how these LCR circuits can be mapped into cavity QED systems, AMO on a chip. Then I'll explain how we turn these circuits into multi-qutrit processors. I'll show some work on how we studied the scrambling of quantum information with qutrits. And then finally, I will tell you about the work that is going on now in our group in Rochester to further study multi-driven systems. All right, so this is an example of a superconducting chip. This is the chip that we made at UC Berkeley. I asked PowerPoint to make it very flashy. It's actually square, 1 by 1 centimeter. It has many of these elements. It's made of superconductors, niobium and aluminum, patterned on silicon. It doesn't have these colors. I just added those for reference. I will explain the elements just in a little bit, but essentially every blue-orange system here, you can think of this as an artificial atom in a cavity, and the atom that we have is a transmon circuit. Why is it interesting? Well, we like to think of it as quantum optics. I know from Rochester, you're very sensitive about the optics part. It's not visible light, it's microwave photons, but the Hamiltonians are very similar, just in the gigahertz regime. And it's special because you can get extremely strong coupling, just because you can capacitively couple these elements together, and you can go into strong coupling regimes that many of the traditional AMO experiments have not been able to reach or have trouble reaching. It has a lot of problems as well.
Coupling is between the radiation field and the atom?
For instance, yeah. So in this case, the cavity here is this orange thing that I'll talk about in just a second, and this is the artificial atom. And the coupling term in this case is really modeled as a capacitor. So it's a capacitive coupling between this capacitor plate and this line right here. And the structures, we call it nanofabrication, but it's barely nanofabrication. The distances are in the order of hundreds of micron or something, or maybe 1 micron. And that is, I want to be very careful not to say easy, but it is not pushing the limits of technology. Again, it's still hard to make, but it's not pushing the size limits in any way or form.
The wavelengths are long, right? They're microwaves.
Absolutely, yeah. Yeah, which is actually quite amazing if you think about it. So a lot of these structures are actually smaller than the wavelength of the excitation. So the transmon itself is actually sub-wavelength, but it still supports these modes, which is pretty cool if you think about it.
Quarter wavelength resonator?
Yes, these are quarter wavelength resonators. Yeah. So actually, that's my next slide. This is a quarter wavelength resonator. Thank you. So we make it as a coplanar waveguide. So you can kind of ignore the wiggles. That's just to make the form factor a little bit more compact. It's not. It doesn't have any other than making a small form. It doesn't have a function. And so if you look closely, this is an example of a waveguide that we have. So there's a center pin and there's the two ground planes here on either end. It's connected to this resonator here, which has also a center pin and two ground planes, forming a coplanar waveguide with two boundary conditions. You'll note that there's a short here on this end, there's an open here on this end, and then you come up with your favorite analogy of a cavity, string, mirror, whatever. It forms a lambda over 4 resonator, and this is actually a simulation that my student me at Rochester did that shows the density of the electric field on the two ends, and you can see that it makes a lambda over 4 resonator. We then represent this as a lumped element circuit, as an LC circuit. So you can think of it in circuit language as well. That's been fairly useful. So then, slowly easing into this, how do we measure this in a lab? Well, this is a cutout where I just cut out all the other elements. We have 8 of these resonators, coplanar waveguide resonators, coupling to this red thing right here. You can kind of ignore this feature right here. You can, for all intents and purposes, think of this as just a transmission line that's reflected here. So we put this in a fridge, cool them down to 10 millikelvin. We hook this up to what's called a vector network analyzer that sends variable frequency microwave radiation in. It goes to the waveguide, it reflects back, interacts with all these resonators. We have a circulator to direct the reflected light. Here we amplify it, we analyze it, and we measure the amplitude and phase response of the reflected microwave signal that I will take the liberty to call light every once in a while. I hope you don't get offended. I know some people do, but I like to think of it as light sometimes.
We're pretty easygoing here. We're in California. We're not
Okay, good. I like the laid back. I definitely get called out for this every once in a while. Actually, at Caltech I did. So I'm very aware that you cannot see this with your eyes. But so this is what the signal would look like. So you have the amplitude and you have the phase as a function of frequency. And you can see these very nice narrow resonances of the 8 resonators that we made. And while this is a little bit easing into it, this particular sample, the data here is a design from Berkeley, but we actually made it at University of Rochester. So doing this in the pandemic, in nano, we were quite happy with this. And as you can see, the internal quality factors, which represent the loss, are in the order of 10 to the 5, while the coupling to the waveguide here is 10 to the 4. So this is a Q factor, so that means lower number is stronger coupling. And that means that you get more signal into your waveguide than that you lose in the resonator, and that's a strong coupling regime. And while this was already we were very happy with this 10 to the 5 number, state of the art can get even higher Q factors. But this was definitely a nice result in our group to show that we can do this. Student Meaty worked really hard on this, and she did really a lot of nice things to get that.
This is local fab?
This was all local fab, yes. Although we have moved on to making, for instance, the thin films. We started to buy them because there was a lot of clean room hacking involved in this. I'm happy to talk about it. It was quite amazing. And made a new mount of the evaporator and things like that. In the end, it is hard. Like to make this really high quality, you want dedicated fab. You can do it. 10 to the 5 is already pretty good. We can work with that. And I'll show some more results of local fab all the way towards the end. Having said this is all, you can describe this classically. This is an harmonic oscillator, not even in a quantum regime yet. So why do we think of this as a quantum circuit? Well, if I take the lumped element representation and I just think of a classical LC circuit, you can think of the magnetic field in the inductor, the electric field stored in the capacitor, and it has this resonance frequency 1 over square root LC, and it behaves as a harmonic oscillator. It turns out that you can quantize this, and you quantize stuff by putting heads on operators, right? The variables now change a little bit, so you can map this classical circuit to, instead of working with the magnetic field and the electric field, you work with the flux and the charge. So it's a flux through the inductor and a charge across the capacitor. And then it turns out that you can describe the system in terms of raising and lowering operators for the canonical variables flux and charge. And you get this quantum harmonic oscillator, and it works out nicely. Now you cool this to the ground state by putting it in a dill fridge. it can relax to the ground state because the temperature, the effective temperature of 10 millikelvin is much lower than the transition temperature going of the resonance frequency, which is effectively a few hundred millikelvin. But it's still linear. So you can only prepare classical light states in harmonic oscillators. So to get the very nice quantum features, you want to add nonlinearities such that you can prepare non-Gaussian states in this oscillator. And the trick that people have used, although this is changing nowadays, so people are using different things, is to add what's called a Josephson tunnel junction, which is a slab of aluminum connected to another piece of aluminum with some tunneling barrier. Aluminum oxide is often used because you can just let oxygen into your chamber and it forms naturally. And this gives you a nonlinear inductance that we give this symbol, this cross, and then two ways in which you can encode a qubit. Initially, what people have done is actually in these flux and charge degrees of freedom. And I'm showing this here because then microscopically, you can have a better, or at least I can have a better idea of what these quantum states are like. Because later I'm going to move to a different circuit where that becomes a little harder. But your degrees of freedom for the flux qubit can really be current circulating clockwise or counterclockwise, where your qubit is flux pointing up or down. Or charge being on one end, or individual electrons or Cooper pairs being on one end of the capacitor or the other end, and that being your qubit. So those are the flux and the charge qubit that worked, but not very robustly against noise. So people started to play around with this circuit, and this is the design that they ended up with. It's called the transmon, in this case coupled to a resonator circuit. And it very much looks like this Cooper pair box, but you tune it into a regime where you store much more of the energy in the Josephson junction, EJ, compared to the capacitor. And it turns out that you become much less sensitive to noise. I can talk about that later if you want to, but this is now the standard in the field. And you can recognize the circuit by these purple things that are the capacitor paths, shorted by this junction here that you cannot see. And this is the only nano thing that we have in our device, and it's a few hundred nanometers. It's the tunnel junction that gives us the nonlinearity. Stick these two together capacitively, right? So there's a capacitor here connecting them, and that just comes from the distance here. So that's an effective capacitive coupling. And then you can tune them very far off resonantly, and you get this dispersive James Cummings Hamiltonian, where I have the cavity term, I truncate the nonlinear oscillator to the lowest two ground states. I can describe this by qubits, and you get some coupling term to do readout. And so this has been the workhorse of superconducting circuits for the longest time. Essentially, you get an atom in the cavity on a chip. Right. So then if we want to control these, we excite this system with a microwave control pulse on resonance with the 0-1 transition. You generate the rotations of the Pauli matrix. You can logical gate, you get Rabi oscillations, you pass them at the right time, you control your microwave pulses, you make it one computer. I'm showing this because later I'm going to go to qtrits. This is a nice reminder slide for you, hopefully. Nowadays, there's many different ways in which people try to improve this. Companies like Google and Rigetti, and also in China, there's companies doing this, make up to hundreds of qubits. They have lifetimes, they have gate errors. And if you're in the business of making quantum computers, you want to make these circuits better. And you can do this by maybe making the materials better. You can come up with new designs, you can do error correction. But one interesting avenue that we are now going in is go to higher levels. I want to point out that one thing that people do in Yale, for instance, and is doing this in linear cavities, which is called bosonic encodings. We are doing something similar but different because we are thinking of a very nonlinear system where we go in higher dimensions. And actually one advantage that we want to explore as well is try to see if we can now encode these cat qubits in nonlinear oscillators, where the cool thing is that now we can control every individual level. So that's another thing that we're looking into. But for now, I'm just going to tell you how we turn this into a qudit, or a 3-level system to start. So the very first trick that we need to play is frequency multiplexing. But this is the Berkeley processor that we did our initial results on. So it's an 8 qutrit system, or a transmon system, where I just copy the same individual model 8 times, and then notice that the only element that I didn't talk about is this coupling resonator that allows us to do entangling gates. Just for the sake of time, I'm not going to talk too much about entangling right here, but we can do it. They capacitively couple, you can do it in many ways. And these are some numbers in case you're interested. I can flash that later for the experts. Turning this into a multi-level system mostly requires multiplexing of both your readout and your control. So instead of sending a single frequency pulse here down the control line resonant with the 0-1 transition, you can also shine light illuminate with microwave radiation on the 1-2 transition simultaneously, turn these pulses on, prepare it in the first excited state, and you get these Rabi oscillations in a 3-level system where you swap population between all 3. And now already you have your 3-level dynamics. If you tune your resonator in the right regime, between the coupling chi and the loss kappa, you can actually observe the reflected light of all 3 of the transmon states by reflecting the light of the cavity. Going to higher levels will require some work, but it's mostly multiplexing to start off. Is that everything? Well, no, because now you have to start to understand how rotations in 3-level systems actually work. And this is, to me, where a little bit of the fun comes in, because, you know, people are often familiar with the 2-level systems, but this is like a fun extension, at least to me. The generators of rotation for a 3-level system are the Gell-Mann matrices. Here I plot them, and you can recognize, I want to think of them as like qubit-like generators of rotation, just in the 0-1 and the 1-2 subspace. So this one very much looks like a Pauli X, but then in the 1-2 subspace. Similar here, there's like a Pauli X-ish operation, but in the 1-2 subspace, and this is the Y. And so if you have microwave transitions driving these individually, you can implement these generators of rotation. Similarly, these 2 Gell-Mann matrices are diagonal, and it turns out that you can actually do diagonal gates or rotations in the qubit subspace just by adjusting the phase of your control. Because the phase determines whether you drive along sigma X or sigma Y. If you change that phase, you can actually also think of it as like a rotation. It's a different way of rotating. It's a change of perspective that is very nice for experimentalists, because all you have to do is update the phase on a very highly controlled microwave tone. You control with very high precision, so it's really high fidelity gates. And you get both of them almost for free, just by playing around with the phases of your microwave drives. The final 2 that I didn't highlight here are drives of the 2-0 transition that you could do in principle, but you don't need it, because you don't need all the rotations to generate a full set. Similar with the Paulis, if you have, for a qubit, if you have X and Z, you can get Y for free. And we don't like to drive it because it requires very high power, because it's forbidden transition. So we stay away from them and make them effectively by stringing together rotations. That's not the full story, because what we would like, if we want to do this Gell-Mann matrix number 4, for instance, is this control Hamiltonian right here, where we only drive the 1-2 transition. But that's not completely what we have. What we have is this bosonic charge operator that is continuous. So in the doubly rotating frame of the 2 transitions, that operator that we actually apply when we irradiate looks like a resonant drive in the 1-2 subspace, with an off-resonant drive term rotating at the frequency of the enharmonicity, which is the difference between the 0-1 and the 1-2 transition. So it's the nonlinearity. And while usually you can throw away these rotating terms if you're in the right regime, in this case, the drive frequency omega is large enough such that it doesn't cancel out compared to the rotating term, the enharmonicity alpha. And so this becomes an error. And it actually off-resonantly shifts your level and also leads to leakage. And in qubit land, we have already known how to deal with this, because now you pulse shape. You can think of this as, if you do a square wave, you get a very broad frequency response of your pulse. And if you Fourier transform it as a Gaussian, you can make it more narrow. And this is called drag, and it works nicely. But this doesn't work for correcting for a phase that you acquire on your second level. Qubit land, nobody cares about it because they don't populate it, so it's not in your computational space. But in qutrit land, all the phases that we acquire due to dynamical star shifts are actually important. So what we did here is a calibration sequence where we apply a bunch of these pulses and we monitor this extra phase by preparing this qutrit state in a superposition. It's like a Ramsey type of experiment where we pick up on this little phase as a function of the number of pulses that we apply, and then on the vertical axis here, we apply a small phase correction, and we see that for this particular phase correction here, doing more pulses doesn't give us an additional phase. So that's how we correct for this dynamical star shift. Little very first thing of how you think about what happens if you start to drive multi-level systems. And very similar physics is going to come back in the final end of my talk, because in the end, it turns out it's always the same problem. You have rotating terms that you want to get rid of. Very often the problem in quantum engineering world. So that gave us these single qutrit gates. The way that we make them the logical gates are this I, X, and Z. The X here is an extension of the bit flip, which actually just adds 1 cyclically to your qutrit state. So 0 goes to 1, 1 goes to 2, 2 goes back to 0. And these are the Pauli gates. There's 9. And we make them by decomposing them into native Clifford rotations in the 0, 1, and the 1, 2 substates. So you string them together, and then effectively you can do any rotation in the qutrit land that you want to. We characterize this with randomized benchmarking. It's a little bit technical, so I can refer you to this paper if you're interested. But what we do is we string together a randomly chosen set of these operations that we then, with a final rotation, undo. And then ideally, you didn't change anywhere. But if these pulses have errors, you start to degrade your system. And this is a very nice pulse-independent way to measure your pulse errors. And we show that we can do this for qutrits, which hadn't been done before. You can then do a different sequence that allows you to see. So this is, in this case, you characterize the average gate set fidelity, but you can individually look out at which pulses cause you the most error. And as you might have expected, it is mostly the 1, 2 subspace rotations because they have less coherence. But the pulses are almost coherence limited. And it is actually quite high fidelity control. Single qutrit rotations are not everything. You want to be able to entangle. We can do a microwave driven pulse that has some problems, and therefore we only use it for initialization. So we can make qutrit entanglement, which is something that's called the cross resonance gate. And here we do state tomography of the canonical entangled qutrit state, for some reason called EPR, Rosen state. 0, 0 plus 1, 1 plus 2, 2. And this is state tomography to show that we can do it with quite high fidelity. So it works. But it's not a universal gate that we use here. You see that's error terms. And so for that reason, we actually use a different trick, which is the 2 qutrits have a static interaction due to the capacitive coupling. If you want to, you can think of it as 2 spin 1 dipoles interacting with each other. If you let them evolve, they will actually naturally entangle. But to make them entangle exactly in the way that you want to make a gate out of it, we do this dynamical decoupling protocol where we locally shift the populations around. And then by changing the way that we shift them around and changing the timing, we can actually exactly make any gate we want to. It's an arbitrary diagonal gate we want to, which is pretty powerful. And then as in qubit language, this is one of my favorite things that I learned about qutrits, is that you can make a qubit C phase into a C naught by sandwiching it with Hadamard's. Same thing is true for qutrits. I really like learning that. So we can make a diagonal C phase gate, a very particular one, that if we sandwich it with Hadamard's, we get the C sum gate. And that is the gate that at the end we characterized with randomized benchmarking here. In this case, it was 85% fidelity. Berkeley later found a way, when I was gone, to start shift these levels a little bit more, to tune the effective dipole interaction, to make this a faster gate. And they proved this to 95 or 97% fidelity or something quite recently, which is really quite cool. Yeah.
What Hadamard are you talking about? Is this like a qutrit Hadamard?
This is a qutrit Hadamard that I will actually talk about towards the end. So I'm going to show it and I'll, yeah.
And what gate length, like duration?
Yes, okay, so I took this out because I thought it was a bit technical, but in this case it's 1.5 microseconds. It is definitely the con of this particular gate that it's slow. Berkeley sped it up, I think, a little bit. I would have to look into the paper, I can give you a reference. I think it's more in the order of hundreds of nanoseconds for them now. So it's definitely a problem to look into. Yep.
Machiel, could you remind us what the controlled sum gate does?
So what it is the mathematical definition is right up there. So you have a control and you have a target. Control is on the left and the target is on the right. And it is a natural extension of the C naught. The way I like to think about it is it adds the number of excitations of the control qutrit to the target qutrit. So you apply, how do you add something? You apply x because it adds, right? And so you add x to the power n to the control state n.
Sorry. What is x? Is it the Pauli x?
Yes.
Or is it?
So x is this Pauli x, which is
It's the qutrit Pauli x.
It's a qutrit Pauli x.
Okay.
Yes, perfect. So it is the addition. I like to think. So it's funny for qubits you think of it as a flip operator, but I started to think about it as a cyclic raising operator, which in qubit land is the same thing, but in in qutrit land it's different because it's not a flop, it's an addition.
It's a mod 3 successor.
Yes, exactly. So you do that, and then the number of things that you add, the number of excitations that you add depends on the control. actually, with showing, so actually on these benchmarks that we have, we showed them with randomized benchmarking as well. So we actually extended this standard technique of characterizing pulses to qutrits for 2 qutrit gates as well. So then technically this shows that we can do universal qutrit control. We made our processor. Let's do some physics with it. The problem that we chose is to study the scrambling of quantum information in 3-level systems. I call this a many-body physics question. Technically, it's a few-body physics question. Actually, it's a 2-body physics question in this case. But because there are 3 levels, it's a little bit more complex. The scrambling of quantum information is something that's recently attracted attention. It connects to black hole dynamics. It connects to solid-state physics. And it is a many-body phenomenon that people are interested in. And maybe someday, if we can make really big, interesting quantum systems, we would want to simulate. For now, we just want to benchmark our system on this particular problem. And the way I like to think about it is that if you have a many-body system here localized by sites with a dot, and you maybe have some quantum information encoded, depicted by something orange that's local, a scrambling unitary will evolve a system from this initially localized state to a delocalized state where all the information is shared between the many-body elements. I will get to a very more rigorous definition in just a second. But what we set out to do is that there was this teleportation protocol brought forward by some of our colleagues that allows you to verify whether you have scrambled quantum information or not. And that's what we set out to do. It turns out to be a 5 qutrit scrambling algorithm that we ran on our working chip. And the scrambling itself is between 2 of the qutrits. So the definition that we took of our scrambling unitary is that a unitary operator U is a scrambling unitary if in the Heisenberg picture, where you think about how does this unitary evolve operators, every single local Pauli operator is mapped to a 2-body operator. Mathematically, I write it down on the left here. So you have in the Heisenberg picture, you look at how all these single body operators on the left and the right hand evolve, and they become, in general, they can be a sum of any of the 2-body operators. In practice, this is a Clifford scrambler. So actually, it turns out that it's going to be, for this particular scrambler that we implemented, the C's are going to be 0 for everything but one of the operators. So every local operator is going to map to one 2-body operator. Graphically, I depict it like this, where if you have a 2-body system, Paulis that start off local, so you have identity on the left or identity on the right, end up non-local. Yeah? Yes?
It could be a very stupid question, but does it have to do something with Lyapunov exponents or like classical scrambling? I mean,
Okay,
is there a connection between this quantum version and the...
Yes, I think there are connections, but
We can talk about
Okay.
I don't think that in this particular case, how we do this here. So, okay, one thing that I should say is that we are not looking at time evolution. We're just looking at applying one unitary operator. So in that sense, there's not really this idea of evolving time. There's no real time evolution under Hamiltonian that is scrambling. Because in the end, what we do is it's a gate, so it's some complex rotation in a 2 qutrit dimensional space, which is periodic, like we just done that. Which is definitely a limitation of the way that we study this, right? But if you go to a many-body physics system, then that would go there. But in principle, there are connections, yeah. But this is a limitation of what we do here. So the scrambler looked like this. If you want to look at what it does, it brings 2 qutrit states ij to the state 2i plus j, comma I plus j. If you have this definition of a scrambler, you could check for yourself that all these local operators get mapped to a single 2-body operator. And what made us really happy is that the decomposition of the scrambler that our collaborators found was exactly 2 C-sum gates applied in with the control and the target split. So we already had the tool to make this scrambler. And we set out to first characterize the scrambling unitary by doing the dumbest thing that you can do, which is full process tomography. I say that this is dumb, but actually it's quite an impressive experimental effort to keep your system stable because this just takes a lot of time. But it gives you beautiful pictures, so I'm going to buy it. It's not a scalable method, which is why we did the scrambling later. The way I think about qutrit process tomography in this case is actually slightly different than people usually will plot it, because from a full process tomography set of data, you could in principle recover the full unitary or even the full non-unitary evolution if you want to. But if you plot this by plotting what's called the Pauli transfer matrix, it has a very nice input-output definition. The full basis of a 2 qutrit subspace is 81 by 81. I chose to here show only 18 by 81 because I took out all the input states that are 2-body already. Because for our scrambler, we're interested in what the single body elements do. And then the way that I read this Pauli transfer matrix is that if I prepare a local operator here, I can read out what it maps to under the Heisenberg evolution after the scrambler is applied. Right? So this is exactly this decomposition. And then as an example, if you have a local gate, you will see that local Paulis map to local Paulis, as one would expect. This is actually data and an experiment showing that we can do this quite well. If you instead insert an entangling gate into this procedure, you will see that some of the individual local Pauli operators start to become mapped to many-body operators, but others actually remain local. So it's not scrambling, but it is starting to spread out. You start to get entanglement. If now we do the process tomography for a scrambling operator, with everything that I told you, you can in a wink see that this is scrambling because the left square is completely empty, which is telling us that all the local operators have been mapped to non-local operators. That was the definition, except for identity, of course, but that's the definition that we started with. And so this visually shows that we have scrambled this quantum information. We did it with a fidelity of around 85%, I think, limited by the C-sum data.
Can I ask you a question here? So if I have this notion of scrambling, if I have an egg and I scramble it, and I scramble it some more, it remains scrambled. If you continue scrambling, if I keep applying this reverse C-sum again and again, does it remain scrambled or does it go back over to the left quadrant?
I have thought about this yesterday and I've not gone back to check it. And I am, by my gut feeling, tells me that it will unscramble for some periodicity, but it's not necessarily obvious to me that okay, there exists an unscrambler unitary, that's for sure, but that's true for your egg as well. But I would guess that there is a periodicity with which it unscrambles, but I would have to go check. And actually, based just on this definition here, you can just insert, right? You could insert this one into itself and then check what the periodicity is.
A related question. Just in the qubit case, this seems similar to encoding to a bell basis to me. Is this like the qutrit generalization of that?
No, because in a qubit, 2 qubits, you cannot define scrambling in a meaningful way.
No, but I mean the operation here.
The encoding in a bell basis is actually a single C-sum. So the half of the scrambler in this case is what you would do if you encode in a bell basis. And then if you do this for a qubit, I would have to think. So if you apply the reverse C0 on a bell state, what happens? Actually, you go back.
Okay, go back to different bases.
That's how we do teleportation.
Yeah.
Well, but that's more qubit.
I'm just asking because this is kind of a generalization of the C0 in a way.
Yeah.
It's like a C increment.
No, but I think if you do this on a qubit C0, you would actually end up in the ground state again. Right? Even if you switch control and target, it doesn't matter. So I think if you do this in a qubit basis, then you're actually unscrambled again. You're unentangled again.
Right. So adding that one extra level is now non-trivially.
Yeah. Yes. And I will say that you can do this with 3 qubits, and it's done, and I'll give a comparison towards the end. But yeah. Yeah, so I mean, we were really happy seeing this. For me, it was a fun visualization, but we set out to also come up with a more hopeful strategy to start studying this in multi-level systems. And it turns out that if you add a lot more complexity, you can have a less time-consuming way of measuring this. And this is this teleportation circuit that I'll give an interpretation of in just a second. But it is a 5 qutrit circuit where you try to characterize how much you scramble between these qutrits. To actually do it, you need a copy of the system that is also scrambling, and you insert EPR pairs into this. And then the goal is to teleport the state from qutrit 1 here by an EPR measurement. And with successful outcomes of the EPR measurement, recover the state from qutrit 1 on qutrit 5. And it turns out that you can show that if and only if you have scrambled information here, you can get a certain success probability of teleportation.
This
That
is
is
why I
bound
was
for
asking.
scrambling.
It's precisely why I was asking that question about the Bell basis encoding.
Okay.
How do you do teleportation through Bell bases for qubits?
Yeah, and actually, okay, yeah, so that's interesting. So you can decompose. It's fun. You can look at the derivation here by decomposing the scrambling states into the Bell bases between these two pairs, and then I did do it, and it's a little bit of a pain because it's 5 qtrits and there's many levels, but yeah. And so I should say that it's not fully, it's only successful 1/9 of the time, for example. But if you post-select on those, you can get the teleportation, and that gives you a proven bound for how much you must have scrambled. And in general, in a many-body system, the problem of identifying scrambling is that it's really hard to distinguish from decoherence, right? Regular decoherence, which you can think of as scrambling with the environment, but not the controlled scrambling that you're interested in. And the nice thing is that the teleportation protocol allows you to show the difference. The process tomography does it well, but it doesn't scale. So we did this. We prepare a lot of input states on our qutrit number 1, and then we measure the outcome state conditioned on the EPR measurement. And this is the tomography in the Gell-Mann matrix basis, showing for the 12 input states that the average teleportation fidelity is above 0.5, which is the bound for showing some non-trivial scrambling. So it works, but there's errors. I will very briefly touch upon an interpretation where the circuit actually came from, because it relates to high energy physics, which is a little bit of a hot topic that I don't want to touch on too much these days. But it is true that this teleportation protocol came from the inspiration of black hole information paradox, particularly Kitaev and Ben Yoshida, and also John Preskill have worked on this, where they started to think about black holes and they ended up with this teleportation protocol. And if you want to, and if you make the connection that a black hole might also scramble information really quickly, then you can interpret the circuit as 2 black holes connected via a wormhole, where you throw information in one end, it is teleported through the wormhole, and you recover it on the other end. This is very much interpretation. It is where it came from, so that's why I do mention it. But I want to be very careful in saying that we did not make a black hole on our chip.
Unlike other people, right?
But that I don't think you will ever say that you have made a black hole in the quantum computer. But if you're interested in studying the dynamics, and you can start making these systems larger and larger, that then maybe you can start to do useful and meaningful quantum simulations. And I just think of this as a nice benchmark on which we can benchmark a processor on. So that's a plus. I know quantum information, and I got to learn about black hole physics and understand some of this. So that's just super exciting to me. So I'm also a little bit torn. Like, I don't want to take away from that excitement, but I also want to make.
Don't want to get too carried away.
I don't want to get carried away with this. And so there is a lot of recent interest in this community. And I will point out that this Lensman paper from the Monroe group did a very similar experiment in terms of interpretation, but they did it with qubits. And if you think of this as a benchmark protocol of how well your chip and your processor or your simulator can do this, they had an all-to-all connected qubit chain, and they needed 7. So the first advantage, and I think it's minor, is that qutrits require you to do, or allow you to do the same protocol on just 5. But really the advantage is that the number of qudit gates, and I say qudit because it's not a genuine qudit gate that we did, because our EPR measure preparation was only acting in a limited subspace. If we would have genuine qutrit gates, 2 qutrit gates, we could have done this with just 8 gates. If we would have wanted to do this on a linear qubit chain, we needed 54 qubit gates. All-to-all connectivity allows you to do it in 16, but all-to-all connectivity is really hard. So one way I can think about this is that we trade off connectivity with this higher level, and we get a much more efficient encoding of this particular algorithm, where we almost perform at a similar level as an all-to-all 7 connected qubit chip, and that's huge. I always find it really hard to make the comparisons here, because I cannot just tell you qtrits always gives you X much. That just doesn't exist. It depends on the protocol, it depends on your error rates, but overall, I do think that this is an example of the compilation benefits that you get.
But what is the genuine here for? Why do you call it genuine?
Acting in the full qtrit subspace. So when I say this sum, it is actually a control controls on all the three, and the target operation is a genuine qutrit X gate. The preparation that we did was a type of gate that only acted in the 0,1 subspace and not in the 2 subspace. So it's like it's not entangling the whole thing at the same time. And if you string together operations, you can make it entangle the whole thing. But you need to string together these, you rotate a little bit in this subspace, you rotate a little bit in this subspace. Ideally, you do the whole thing together. And that is what our C-sum gate did. But we didn't use our C-sum gate for state preparation because it was slow and lower fidelity. So if you would really have gates that genuinely work, like the gate that Berkeley prepared, you would just need 8 gates. And that is a little bit of the topic of the final thing that I will show you, which is the work we've been doing in Rochester, which is taking this one step further and thinking, how can we now genuinely use the qutrit nature of this system? And we took that back to just a single qutrit problem. So far we have shown that we can do qutrit operations by stringing together these qubit-like operations. And they are universal, but they are slow, and they are still somewhat limited in fidelity. And we took the problem, actually Ray has mostly been working on this, so if you know him, he's my graduate student working together with Zihao, and we asked, can we directly generate a Hadamard rotation as opposed to effectively create it by stringing together qubit pulses? I actually have a qubit example to issue into the problem that we set in. So this is a qubit Hadamard, and the way that most quantum engineers or quantum computing people will make this Hadamard is by doing 2 pulses together. Like I think you do an x 180 pulse and then minus y pi over 2 or something like that, and you get a Hadamard. And there's many different ways in which you can decompose a Hadamard into a sequence of rotations. But any operation in a qubit language can also be thought of as just some rotation on the Blok sphere. For a Hadamard, I don't know if you've ever thought about this, but it is actually a rotation tilted along an angle. So this is how it looks like on the Blok sphere. And you can make it by off-resonantly driving your transition where your Rabi frequency is exactly your detuning. Because in that case, you get exactly this off-plane rotation that gives you the Hadamard. And so nobody does this, but this is the way to directly generate a a qubit Hadamard.
So why does no one do it?
So nobody does it because it's hard to calibrate. We know very well how to calibrate our Clifford rotations. Saying this is Hadamard or Clifford? No, it's not Clifford. So the pi over 2s and the pi's, we have nice calibration protocols. This would be an extra calibration. Also, you can decompose a qubit Hadamard in a lot of Z gates as well. So I think you have 2 pi over 2 pulses and a bunch of virtual Z's. And then it's just fewer calibrations. Saying that nobody does it, I actually did do this in my master project. So that's why I was super excited about it, just because we wanted to see if we could do it. But it's a calibration thing. In qutrit land, there's good reason to want to do this because the decomposition starts to become more and more complex. Also, it is this fun many-body driven system that I talked about in quantum optics. So this is the qutrit Hadamard. Note that you need all these off-diagonal elements here. And I will say that there's one way to do it relatively easily, which is if you just directly drive the 0 to 2 transition. People have done this, but we don't like it because it requires high power and it's problematic for that reason. But lo and behold, without giving you the intuition, there exists a protocol where you directly drive the 0-1 and the 1-2 transition off-resonantly. And if you do it for these particular parameters, it turns out that you do get the exact qutrit Hadamard just from, and you directly implement it, so without stringing together pulses. Intuitively, why do you get this 0 to 2 transition? There is a hand-wavy connection to a protocol that you might be familiar with, which is stimulated Raman adiabatic passage, where you also off-resonantly drive one level when you want to transfer population from, so you can think of this, it's usually as a lambda system, but if you drive population, you want to do it from 0 to 2, styrep would be off-resonantly driving this transition to transfer from 0 to 2 without ever populating 1. And that is exactly getting this off-diagonal element here. Now we want to have something that creates a superposition, so we want to have all of them at the same time. But I think the analogy stands. So I think it's a really fun quantum optics problem that theoretically was solved here, but we wanted to do this experiment. So we actually, this is what you need to do. You need to off-resonantly drive the 0-1-2 transition and the 1-2 transition with these particular parameters in terms of gate time and detuning. And then if you would have this, if you can evolve under this ideal Hamiltonian, and you stop it at a particular time, the unitary evolution that you have got at the end is this Hadamard gate, and this is how the evolution would look like if you start in the 0 state. So you can see naturally everything drives towards this equal superposition. Right. So we tried to do this on a chip that we got from MIT Lincoln Labs. These are some parameters. It's a new collaboration where we give them designs, they give us chips, which is really nice because we can play around with the parameters. But when we did this, we saw something similar but different. We did see that we can get to this kind of superposition here, but we also see these additional wiggles going on, and we also see that we kind of overshoot. So there's something going on here. There was a problem with this particular dose. I've already given you the answer because it's the same problem that I talked about in the beginning. This is actually the fact that our operations are not just driving the 0-1 transition and the 1-2 transition. We have an error term here that is consisting of what we now call these cross-drive terms. So if we want to implement the 0-1 transition drive, we have this off-resonant term here, as for the single qutrit case. But now we do both of them at the same time. So the 1-2 transition that we want to drive here also gets these off-resonant terms here that again start shift and cause leakage, and it's a problem, and it causes all these wiggles where the periodicity here is actually exactly the anachronicity. So we understand very well where it comes from, and I should note that one way to get rid of it is just go into a regime where you can apply the wave approximation that makes your gate really slow. So, or you make the anachronicity really high, which has other design issues with the chip. So at this point I told Ray, just do pill shaping and we'll be done with it. And this was about a year ago, and this is where I learned a very valuable lesson as a PI that some problems can become much more tricky than you think they are. And so we have been studying this problem for a long time, and finally there's some nice results now, and we can talk about some of the technique that we use, but it's just really tricky because some of your approximations don't work. It is a really difficult problem. If you are at March meeting, I encourage you to hear Ray talk about this. I will just tell you that he found that you can do what's called a magnet-stator expansion, which is kind of a running average that will, to some degree, approach the dynamics, even though it's a perturbative method that doesn't work fully. And it gave us some hint at some of the error terms that, if you have seen this before, it actually looks like a drag type of Pills error that he then found a way to correct by implementing these numerical optimizations of drag-like pulses. And this is both work in progress, and Ray has actually just yesterday sent me nice data where we can start to see this. So I encourage you to go to March meeting and talk to Ray, because this was really a very nice project to learn how to do pill shaping in three-level systems. And I'm very excited about this right now. It's quite cool. So Ray did excellent work there. With that, I will give just 2 more slides showing an outlook on how we plan to climb the transmon ladder further. I think that what we learned on pill shaping in 3-level systems is really nice when we go to higher level systems, right? Maybe it's a very small problem right now, but if you go to these multi-level systems, these terms become important. And so I'm hoping that we can extend that. The very first thing to worry about is the noise. And the very first thing that you can never get rid of is the bosonic enhancement, which comes from the fact that your raising and lowering operators have this square root of n term in there, which just means that your decay rate for higher levels is faster. This is not specific to the transmon, this is specific to bosonic operators. So this is true for bosonic codes as well. So I definitely got this criticism of like, oh, but you have lower T1, and people maybe don't realize that bosonic codes have the exact same problem. I like to think about it as that you're just more likely to use 2 photons because you only lose only 1. So it's more likely to go there. That's my classical version. But it works out. It's bosonic enhancement, T1 gets shorter as you go higher. But that I think you can get around by having also faster gates, because the pro is that you also interact fast. The phase noise is a little bit more of a problem. This is a little bit technical to the transmon, but it turns out that you need to go higher and higher in the EJ over EC ratio to suppress the charge dispersion for higher and higher levels. So if you encode a qubit, maybe an EJ over EC of 50 is enough. If you encode a qutrit, maybe you need 70 EJ over EC to get this charge dispersion, which is how much levels fluctuate in the phase, on the order of a few tens of kilohertz. And then the higher level you go, the higher you need to go in EJ over EC.
I think it's because the energy level is not stable, like the higher you go, right?
It's broadening from the periodicity.
Yeah. So you get this periodicity in charge, the charge variable, where it starts to fluctuate. And the story of the transmon is always you can exponentially suppress this by going to higher EJ over EC. but it's also, I don't know if it's exponential or like some power law. It gets worse again if you go higher. And you can counter this with the exponential scaling of the EJ over EC. If you fix your qubit frequency, you lose at one thing, which is the thing that I just talked about, which is the anharmonicity. So that is the downside. You become less and less harmonic. You become more and more like a harmonic oscillator. In one limit, I don't think it maps to the limit, but I like to think about it that in the end, you just have your linear oscillator again, and you lose this ability to control. But now your anharmonicity terms, which were the exact error terms that I showed earlier, become the problem again. So this is a trade-off that we like to explore. I think we have some wiggle room, but in the end, we like to move to a different circuit that doesn't have this fundamental problem. And there is this thing called an IST, an inductively shunted transmon, that just has a different spectrum that doesn't suffer from this trade-off as much. And the trick is that you stick a very big inductor to your transmon circuit, and then if you work out the noise, it is more forgiving. So that's something that we are exploring. And the first thing that we need is this very large inductive element. And while you can make this with a lot of junctions, this is a linear inductor, but it also has a very high impedance. And we started to make these what we call spiral resonators. This is again data by Machiel from UR, where this is a spiral of I don't know how many lines, like almost 100 or something, separated by, now it actually becomes more and more nanofab, because these are maybe 100 nanometers wide features. But me and Liz have shown that we can make these with fairly high Qs. And we also like to use these to start coupled to gate-defined quantum dots together with Professor John Nichols. This is a joint collaboration that we are looking at, both for hybrid quantum systems and for these new systems to go to higher and higher levels. So that is what we have going on. That's the things that we are excited about in Rochester. With that, I can acknowledge that a lot of this work was done at UC Berkeley and our theory collaborators at the Perimeter Institute and our group here at University of Rochester. This is actually an old picture of the fridge. It's moved already 3 times by now. So if you're back in Rochester, I can show you our new lab. It's quite exciting. We have a few PhD students working. With that, I'm happy to take any questions. Thank you for your attention.
So you're in your own lab now, Machiel.
Yes.
All right.
John Howell's former lab. Is where I landed.
Excellent.
Did you get both halves, big space, or did they trim you down?
So this is the other half,
Okay.
where now John is there right now. I promise that I can go there if needed. But they also gave me space on the 4th floor where they built a dedicated clean room where we hope to make our own junctions. So that's the one thing that we cannot do in-house yet, because it requires this special angle e-beam evaporator to make the, like you make one end, then you make the other end. It's you can think of it as Manhattan. So I always like to think of you have the sun in Manhattan along the avenues, and then you make aluminum where the sun is, and you rotate Manhattan, and now you make aluminum where the streets are, right? And that way, so now you have a lead of aluminum and you can make it perpendicular. And if in between you let some oxygen into your chamber, you get aluminum oxide and you have your junction. But that requires evaporation and rotation, and that's just usually not available. So that's a tool that I need, and we're making it in Rochester. And, that's going to happen in the summer, so we're excited for that.
What about 4 levels?
Yeah, so I mean, I think actually 5 is already feasible. The data that I showed is actually a relatively low EJ over EC chip.
Yeah.
And I think we can get to higher EJ over. I mean, okay, we know we can go to higher EJ over EC, but I think we can also do our pulse shaping such that even with an anharmonicity of 175 megahertz, we can get decent pulses. And then I think a qquint, so a 5-level system, is not very far out of reach. The nice thing is that we have these chips from MIT Lincoln Labs. So we design it, they make it, they get very high coherence, and as long as your design is right, the fabrication, they won't mess this up because they have like an industrial size clean room. And so I'm optimistic that a few levels higher we can get.
So are you playing with the thickness of the junctions or the gap between the capacitances? How are you altering this ratio? Physically?
Yeah, so the way that I like, there's many ways in which you can go about how you think about this, but you need a very, so the anharmonicity is set by the EC, roughly. So if you translate the energy in the capacitance to a frequency number, then you with a factor of something, you get your anomalisticity. So you change the capacitor size to fix the anomalisticity that you want to, and then we adjust the thickness of the junction or the width of the junction, actually both a little bit, to get the frequency that we want for that anomalisticity, and then that fixes our UJ over EC. So we play with both. It turns out that we need less of a capacitor gap, and then that is a little bit of a design problem, or not problem, but like you have to then design for lower microwave radiation loss, and you also change where the field is, and people have optimized these structures a lot to minimize the overlap of the field with all the lossy materials. And so when we chase this capacitor gap, we need to revisit that and optimize that structure such that the field lives in the least lossy materials. So those are things that we are looking into, in like what's the geometry that fits this best, and that, I mean that's the research that we're also doing. But it's all within reasonable fabrication things, and you need some higher bandwidth to do the control pulses, right? And then you want to avoid frequency overlap. And there is something with the readout that Sasha actually has some work on. So you get these resonances of these higher levels. It's actually pretty fun physics as well. And that may get a little bit worse for higher levels, but yeah, I think at least for a few, we are good. I will say that at some point, this is the potential. There is a limit to how many of these levels you can fit within your cosine potential.
Sure.
And I like, we're not going to go very, like 10 is going to push it.
Right. So I have a follow-up there, because you talked about adding this inductor, which adds this kind of quadratic shift to the baseline, right? Is the intuition there of why that'll help that it reduces the periodicity, so it's going to reduce the like level broadening, or is there another intuition that you're using there?
Oof, that's a really good question. There must be an intuition, but I don't have it.
Because that's what's coming to mind, is if it's a flat cosine, then you get like the periodic potential, so then you get the level broadening to bands, right? But if you break that periodicity with it.
Well, but I mean, so the other thing is that I'm plotting the phase variable now, right? Whereas the charge noise actually is in the charge variable. So for the transmon, it looks very flat. Like if I make this plot as a function of the charge variable, then for a transmon, it starts to look really flat, like flat lines.
Right.
And I don't know how to think about the intuition, because you can expand the Hamiltonian in terms of like an n squared term plus a cosine phi term.
Exactly.
And we're looking at the cosine phi term, but I don't know.
But now you're adding a quadratic piece to it with the inductor.
Yeah, but then what, I don't know. So that's the phase variable.
But what I'm saying is that the energy levels, they broaden because they become energy bands when you have a periodic structure. As you go up the cosine potential, because the width of the tunneling between the adjacent wells is narrower, then the bands broaden more. But here, by adding that quadratic, you're sort of changing the periodic structure, that fixed energy.
So I think, I mean, that's true. I don't disagree with that. But an interesting feature is that we're also looking at the charge noise. So I don't know how to translate this into what happens to the charge noise. Because in the end, the statement I'm making is that the charge noise is less.
Right, but the charge noise comes from like a gate charge external to the circuit fluctuating, which is taking it up and down inside one of the energy bands. So if you narrow the energy bands, you narrow the fluctuation. Anyway, just a thought, because I was curious why you're using such a weak quadratic here.
Oh, and also, I mean, this is not, I took this from the paper that is listed here. This is not necessarily optimized for it. And there's also a connection to a different regime, although it's very similar, called the fluxonium.
Yes.
Where actually, if you now, originally people were thinking about encoding your qubits in these different bands, and that's supposed to be a really long-lived qubit. And that's why people started to study this. But then we think that you can get very nice properties of the higher levels as well. So it's a little bit indifferent. But I would love to talk more to get more intuition about these circuits. It's
yeah, I was just interested, you're calling it not fluxonium on the right, and I think it's because you're keeping it in this regime of a very weak parabola, as opposed to fluxonium that can have much steeper.
Yes, I think that's right. And that's actually, so a fluxonium you can think of as an IST with a very low EJ over EC. Actually, the paper has a very nice plot of it's difficult because you have three dominant energies. You have the junction, the capacitor, and the inductor. So all the ratios, everybody plots different axes of the ratios between the three. But the difference between the fluxonium and the IST is that you're in the very low EJ over EC limit. Yeah.
All right, any other questions? Okay, Taga?
Yeah, I was just wondering how easy it is or difficult it is to scale up the qutrit system to like 100 qutrits.
Well, easy for who?
It's hard to do that for qubits, right?
For experimentalist or
Yeah, but what kind of experimentalist with what kind of? I mean, this is a really difficult question because I think that the technology is close enough to the existing qubit technology that if you would now give me access, but it's just hard to scale up in general, right? So it's hard for me to make a 100 qubit chip just because it requires a lot of control of your fabrication. There's a lot of extra things that you need to make this work. You need bigger chip sizes for which you need through silicon vias, which is all pretty well understood technology, but also really expensive. So, and then you need, many more control lines, which all has been developed. But for me as a research group, it's pretty hard to do that. If you would give me the resources of like a clean room and the knowledge of, say, Google or IBM or whatever, then it's fairly easy. Easy to make that same chip that people now have for qubits, change the parameters a little bit, increase the bandwidth a little bit, and then do this for qutrits. Like that's on the easy side. But the way that this works is that when you start to scale this up, you narrow everything. So you take away every knob to tune. So everything that I change, when you would say I want higher bandwidth microwave electronics, they will tell you, well, we just invested millions in making this very narrow bandwidth, and we cannot do it. And so that's a little bit of a trade-off. If you scale up, you want to narrow your parameter space, and it's broaden it a little bit. So it is a tricky question, but overall, I don't see really fundamental problems. If you go to the IST, for instance, it would be more difficult. But I'm confident that if somebody who has the capability of making a 100 qubit chip, that they could fairly easily make a 100 qubit chip as well.
Okay, any other questions? We on the Zoom? Do we have access to the Zoom chats or questions? No questions? All right, well, let's thank Machiel again for the nice talk. All right, once again, he'll be around all day.